are you doing? Are you collecting the concrete waste?
Yes, it's concrete, but it's no longer a waste. Well, I'm trying to reduce the 3 billion tons of construction demolition waste are being dumped each and every year in the form of landfills, causing landfill issues, biodiversity degradation, and environmental pollution.
How does this even make sense?
Well, I'm going to adopt circular economy principle by recycling the aggregate inside this waste and reusing them back into concrete production.
Is this possible?
Yes, it is possible. That is called Recycled Concrete Aggregate. Let me show you. Hey, is this the same aggregate your friend collecting at the dumping yard?
No, it's not. That is RCA from demolished concrete, but this is natural aggregate from quarry that is commonly used in concrete mix. Natural aggregate production not only displays natural resources but also contributes to environmental degradation.
Well, what's the difference between RCA and natural aggregate? Aren't they both the same?
Let's discuss. Let's compare the aggregates. The surface of natural aggregate are smooth.
The surface of RCA is rough and angular caused by the crushing process.
There are no pores in natural aggregate.
RCA is highly porous caused by the adhered mortar.
There are no cracks in natural aggregates.
RCA has many micro cracks caused by crushing process and also adhered mortar.
Natural aggregate has lower water absorption capacity.
RCA has high water absorption caused by the higher porosity and also adhered mortar.
Since natural aggregate are solid and dense, it has higher density.
RCA has lower density due to the low solid content compared to the adhered mortar attached to the aggregate.
In this case, it clearly can be seen that natural aggregate has better properties than RCA.
Yes, the major drawback of recycled concrete aggregate is caused by the adhered mortar attached to the aggregate surface. This is where our research comes in.
Assalamualaikum. Today I am honored to present a project entitled ReNova Advanced Singular Construction through Geopolymer-Enhanced Recycled Aggregate. The objective of the research have three. The first objective is to evaluate the mechanical properties of 1-part and 2-part fly ash based geopolymer 3D RCA. And the second is to evaluate the mechanical performance of concrete incorporating 1-part and 2-part geopolymer 3D RCA. And the last is to assess the durability performance of concrete containing geopolymer 3D RCA under wet-dry exposure.
RCA treatment is used widely for various purposes. Since the adhered mortar acts as the major root cause for the RCA performance weakness, this study investigates the strengthening of adhered mortar instead of complete mortar removal. Although mortar removal is the widely used treatment methods, strengthening the residual attached mortar in the aggregate surface is less discovered. That is why our study focused on treating the residual mortar attached to the aggregate surface using geopolymer surface coating treatment in order to enhance the RCA performance. Through this study, the major drawbacks of RCA, which are high porosity, high water absorption, and low density, can be completely overcome and increase the performance of recycled concrete aggregate equivalent to the performance of natural aggregate.
This study evaluates the mechanical and durability properties of 1-part and 2-part geopolymer surface-treated RCA. Geopolymer is a sustainable binder because they are consist of industrial byproducts and they can mix with alkaline activator to produce geopolymerization reaction. In this study, fly ash, which is a byproduct of coal combustion, are used as aluminosilicate precursor for both 1 and 2-part geopolymer. On the other hand, alkaline activator used for 1-part geopolymer are water and also sodium metasilicate, which is also known for just add water system. While sodium hydroxide and sodium silicate are used for 2-part geopolymer. When aluminosilicate precursor and alkaline activator combines together, it produces gels that fills the pores and also crack on RCA surfaces, thus enhances RCA properties.
Next slide is a sustainable development goal, which is SDG. ReNova directly support the SDG, especially SDG 9, which is industry innovation and infrastructure by develop an innovative and sustainable construction material through geopolymer technology. It also contributes to SDG 11, which is sustainable cities and communities by promoting durable and environmental environmental-friendly infrastructure. Furthermore, the project supports SDG 12, which is responsible consumption and production through the reuse of construction and demolition waste as recycled concrete aggregate, encourage a circular economy. Finally, by replace conventional material with fly ash-based geopolymer and reduce the demand for natural aggregate, ReNova contribute to SDG 13, which is climate action, help to reduce carbon emission and conserve natural resources. In addition, this project is closely aligned with the National Construction Policy 2030, especially under Clause 2, which is embrace sustainable built environment. ReNova also support the policy by promoting environmental friendly construction, material and strand construction waste management through the utilization of recycled concrete aggregate. At the same time, the project encourages research, technology innovation to develop high quality, reliable and sustainable infrastructure that meet the future need of Malaysian construction industry. It also supports the 12 Malaysia Plan, especially term 3, which is advancing sustainability. The project contributes to the implementation of low carbon and resilient development by reduce construction waste and maximizing the use of industry byproducts such as fly ash. Through the application of geopolymer technology and recycled concrete aggregate, ReNova promotes efficient research utilization and strengthens the transition toward a circular economy, supporting Malaysian long-term green growth strategy.